Sí.
Good afternoon. We are very happy to have here Jeremy Echeverria, who is an expert in beyond standard model physics, extension of the gauge, scalar, and fermion sector theory with extended particle content and several extra gauge and discrete flavour symmetries and theory that address the fermion flavour problem and implication in Charleston revelation, dark matter, leptogenesis. And today, Jeremy Echeverria will talk about strongly coupled inner scalar sector with radiated neutrino masses.
Okay, thank you. Thank you for the presentation. Thank you, all of you, for staying here. Today we're going to discuss about this model. This is a strongly coupled inner scalar sector with mechanism by have radiative neutrino masses and not radiative neutrino masses. Okay, I'm going to split this presentation in 4 parts: introduction, the basics of the model, the results and phenomenology, and some conclusions from this work. Oh, sorry, this work, this presentation is based on this article that we work with Professor Antonio Cárcamo, me, Roman Pasechnik from Lund University, and Daniel Salinas Arizmendi. A standard model is one of the most accurate theories that humanity has been created, but there are some challenges in the description of the nature that standard model have some issues. I'm going to discuss 3 of them. One of them is the neutrino mass. Why, in which form neutrino have masses in the standard model? In the minimal setup of the standard model, the ingredients in order to have neutrino masses are absent, but we know that the neutrino oscillations have been experimentally confirmed. So we know that neutrino have to be mass states, or less the square difference of the masses of the neutrino have to be non-zero. So we must go beyond the standard, the minimal scenario of the standard model. The fermion mass hierarchy. Well, in standard model, all the fermions have is masses using the same mechanism, the Higgs mechanism. The observed masses or the experimental masses for these fermions have a strong hierarchy, and standard model doesn't say us why exists this strong hierarchy. Standard model do not provide a dynamical principle or a principle that explains the strong hierarchy of the masses. And the electroweak hierarchy problem, the electroweak scale is a characteristic mass scale or energy scale of the standard model that is extremely small if we compare with the Planck scale, for example. And the stability of this scale against UV scales or very high energy scales require very strong cancellations and some fine tuning. And again, standard model in its minimal setup doesn't have a dynamical principle to stabilize this electroweak scale. All born from the fermion mass mechanism in the minimal standard model. That is this kind of interaction between left-handed neutrino, right-handed neutrino, and the Higgs field. After the electroweak symmetry breaking around 240 GeV, we have that the Higgs obtain a vacuum expectation value non-different to 0, and the fermions of the standard model acquire masses of this type, proportional to the BEV and some parameters that comes from the interaction, the Yukawa parameters. For example, if we take the PDG, the more recent PDG values, we have that the Yukawa parameters have to be from this wide range of orders. Okay. If we talk again these problems using this mass mechanism, we can rewrite the problems in this form. About neutrino masses, we doesn't have a right-handed neutrino in the minimal standard model, so we cannot create, or we cannot have this interaction of this type, but with neutrinos. So we cannot take put a Dirac mask for neutrinos, and if we go beyond or non-Dirac mask, we can construct a Majorana mask for the neutrino, but the Majorana mask term is not gauge invariant. So the minimal gauge invariant Majorana term is a non-renormalizable operator. So we are beyond the minimal setup of the standard model. The fermion mass hierarchy is related with the order of magnitude of the free parameters, these Yukawa parameters. If we see, for example, for the mass of the electron, we need a Yukawa of the order of 10 to the minus 6. And to the top quark mass, we need a Yukawa of the order of 1. So why this strong hierarchy? The standard model doesn't have an answer for that. And the electroweak hierarchy problem, the value, the vacuum expectation value for the Higgs field have a value, a specific value, but this value is proportional or is related with the mass of the Higgs. The Higgs field is a scalar field, so the scalar fields are very sensitive to the UV corrections or the UV scale. So if there are physics at UV scale, a very high scale, this mass have a strong corrections, a strong quantum correction from this UV scale. So why the electroweak scale is so stable? This is the question. So we need strong cancellations between the UV corrections, or maybe there is no UV physics. I don't know. Okay. What is our proposal? Well, our proposal is extend the minimal standard model through a new strongly coupled sector, this SU2 group that is strongly coupled. Here, the SU21 is the usual SU2L group in the standard model. This extension adds a new strong sector from the standard model. For example, in the weakly sector or standard sector, we have the usual Higgs doublet that in this model we call phi field, and from the strongly coupled sector, we have two inner doublets. This is two scalar doublets that not acquire vacuum expectation value. From the dynamical of this extended group, we have appears two vector resonance, neutral resonance and charge resonance. How we obtain again the standard model, the minimal standard model, through this scalar bidoublet. This is an active scalar bidoublet that acquire a vacuum expectation value and breaks the SU2, the double SU2 group to the standard SU2L from the standard model. So this field allows the interaction between inert sector and the visible or standard sector, right? So here, phi, the H doublets, phi and the H doublets and sigma are composite states, low energy composite states from this underlying strongly sector, right? The model also have discrete symmetries in order to implement mass fermion mechanism. For example, this C2 symmetry, it is spontaneously broken by an active singlet. This is a scalar singlet that acquire a vacuum expectation value. The propose for this C2 symmetry is forbids the three-level Yukawa terms in the standard model for the sharp fermions, except for the top. Later we're going to explain why the top not have a three-level Yukawa term forbidden. And another proposal is to implement a universal seesaw mechanism for the fermions. This C2 prime symmetry, a copy of this C2, is a preserved symmetry. It's not a broken symmetry. And the proposal is to forbid the three-level neutrino masses, right? This is for charged fermions, and this is for neutrino masses. We don't want three-level masses in this model. And the another proposal is to implement a one-loop scotogenic or seesaw, radiative seesaw mechanism for neutrinos. The discrete symmetry structure organize the generation of the masses in the fermion masses in the model, right? The scalar phenomenology of this type of models has been studied before. Here there are some examples. Here we have some persons that has been studied these things. But here we are connecting this exotic scalar spectrum with fermion mass mechanism. This is the distinctive the distinctive feature of our model. So the model, some things about the model. The symmetry breaking cascade or the symmetry breaking pattern is the following. A very high scale above 10 TeV, we have an underlying strong dynamics where the SU2, the strong sector, have some dynamics, some hidden dynamic that we doesn't know. But at low energy compared with this lambda scale parameter, we have an effective description of the sector in terms of a nonlinear sigma model that are the fields that we are going to explore. If we go below this energy at around 10 TeV, we have the first symmetry breaking driven by the capital sigma field, this bidoublet, and the scalar singlet that breaks. One breaks the pattern of the double SU2 symmetry, or breaks the strong SU2 symmetry, and the sigma field, the sigma singlet field, breaks the one of the discrete symmetries. In order to have the minimal standard model, where it's not so minimal because we have an extra discrete symmetry reserved from the eigenvalue scale, and also below that energy we have the usual electroweak symmetry breaking driven by the Higgs boson or Higgs field. So in our model, the hierarchy of symmetry breaking is this: the capital sigma bev is bigger than the small sigma bev. Okay. The mass mechanism is an universal seesaw. We have in the charged fermion sector the usual right-handed singlets, the U-type quarks, down-type quarks, and the leptons that are odd under the C2 symmetry, except for the U3 singlet that is related with the top quark. Okay, so why we want to preserve the structure of the top quark? Well, if we're going to the fermion mass hierarchy, we see here that the parameter associated with the mass of the top is the order of 1. So top quark is the only one in the fermion spectrum that have natural mass scale respect to the electroweak scale. So we want to keep this feature in our model. So we doesn't charge the top quark here. But the another fermions are odd under C2. This forbids the three-level masses here. This interaction is forbidden for the C2 symmetry. This is charged under the symmetry, and this one is not charged. So this interaction is forbidden. So we need another mechanism to have masses for the quarks. That is schematically here. We have new vector-like fermions. We have up-type quarks, exotic up-type quarks, heavy exotic up-type quarks, down-type quarks. From the up-type quarks, we have only 2 flavors because we keep the structure of the top quark. And the down-type quarks, we have 3 flavors, also for the leptons. So the mass mechanism is from this diagram. If you see the interaction between a left-handed fermion and a right-handed fermion is given by this effective insertion, right? We have interaction between the standard model fermion with an exotic fermion that is given by this interaction that allows in our model. These are non-renormalizable operators. So we have a natural mass scale suppression for the masses of the fermions that can explain the smallness of the another fermions below the top quark, and the exotic fermions, exotic singlet fermions, have masses with a mechanism like the standard model mechanism, driven by this sigma singlet, right? So in the case of neutrinos, we have a more complex mechanism. Here we have a radiative mechanism. The C2 prime symmetry forbids the terms like this. We introduce a new heavy majorana neutrino. Is that could have interaction with the standard model neutrino in this form in order to have a 3-level mass, but we don't want the 3-level mass because we know that the mass of the neutrinos have to be very tiny. So a natural explanation could be that the mass of the neutrinos are from quad 2 corrections, and this is a good explanation for the smallness of masses. So we forbid this term using this C2 symmetry, charging the heavy majorana neutrino. And this is very cute. The capital sigma bidoublet that emerged from this strongly coupled symmetry allows the coupling between this strongly coupled sector with the inner scalars and the fermions of the theory. In this case, the neutrino. So we have interaction from this type. So the masses of the neutrinos are dominated by this topology, in which we have one loop usual radiative mechanism from like the mass photogenic model, but with some insertions in some parts. And some different thing here is that the inner scalar inside the loop are from this strongly coupled sector, are not SU2L doublets like in the standard photogenic model. So the masses of the active neutrinos are naturally suppressed by this one loop factor and a loop function, and proportional to these interaction parameters between the strongly coupled sector.
May I interrupt?
Yeah.
The scale is the suppression scale. How this scale compares with the depth of the sigma? Is it the same order?
No. There are one order of magnitude at least. Yeah.
Oh, yeah.
So we have a 10 to the minus 1 suppression from this difference. Very good question. Thank you. So the physical spectrum of the model, I was thinking how to show you without a huge table as usual. So I think a small table. So in the C2 prime even sector, we have neutral scalars. These scalars come from the interaction between standard model Higgs bidoublet and the sigma singlet. We have also two CPO states, charged scalars, and these vector resonances that comes from the gauge dynamic, strongly gauge dynamics underlying the SU2 strongly coupled. And in the C2 prime odd sector or dark sector, people sometimes call that dark sector, we also have neutral scalars, charged scalars, and the heavy neutrino. In this case, we have only one heavy neutrino. So the CP even sector have influence in the Higgs physics, in the electroweak precision test, and single and possible signals from colliders. And the CP2, the C2 prime hot sector have influences in the observables of lepton flavor violation and lepton number violation signals. The results or phenomenology of this model, we start with the standard model fermion mass hierarchy. After the symmetry breaking of the sigma field, like the standard model fermions mix with the heavy vectors of the model, and after integrating out the heavy states, we generate effective masses through the universal seesaw that we seen in previous slides. The effective mass matrices are of this form. This explains the smallness of and hierarchy of the standard model fermions. And as we say, the top quark remains naturally much heavier with a three-level mass related with the standard model Higgs. The hierarchy comes from the symmetry structure and mixing with the heavy fermions. This is a good feature of the model. And we have here some explanation of these blocks of the mass matrices. We can prove that the parameter space of the model is enough to have all the observables from the quark and neutrino sector. Respect to the vector resonances, that is very interesting here. The vector resonances arise from the mixing between the standard gauge bosons and the new states from the strongly coupled SU2 symmetry. And we have mixing angles between two sectors. So these mixing angles are very restricted by the electroweak precision data. So we have to comprove what are the values for this mixing. We show that the masses of the heavy resonances are related with this C parameter. This C parameter is related with the PEV of the sigma and some parameters of the nonlinear sigma model that have been explored in previous studies, and the strong coupling constant. So if we plot the behavior of the mixing angle and the masses of the resonances, we have here the limit for the mixing with the standard model bosons provided by the electroweak precision data. So we see here that we need pretty heavy vector resonances, at least in this model, and is comparable with the strongly sector scale, right? Respecting to the Higgs physics, we start with the study of the trilineal self-coupling of the Higgs boson. Okay, the trilinear Higgs self-coupling is characterize the shape of the scalar potential. So this is a very important parameter. And when you extend the scalar sector, you have to prove that this new dynamics doesn't have bad consequences for the trilinear self-coupling. We have a three-level contribution, and we also have radiative corrections for this linear coupling. The standard form in which the people study the behavior of this linear coupling is through this kappa parameter, that is the ratio between the beyond standard model prediction and the standard model prediction. And here we have the one loop contributions, the trilineal contribution, and one loop contribution also with the corresponding counterterms. The current bound provided by Atlas and CMS say us that this kappa parameter is between this range. And in our model, if we compute all this correction, we have a three-level contribution in this blue line, around 0.5, and these green points are prediction from the radiative correction. So radiative corrections tends to have a small trilinear coupling. There are studies that compute this contribution from inner sector and extended Higgs models. So we can see that our model is agree with the experimental bounds of this linear coupling. So another important precision test is the Higgs into diphoton rate. We know that Higgs can decay into diphoton final state, right? So we also have to be careful with this parameter. In the standard model, the contributions that have influence on this ratio, in this rate, are mainly the top quark and the W bosons. But in this model, we have extra contribution that comes from the one loop contributions from charge scalars and heavy vector resonances. So there is very important to prove that we doesn't have a strong correction of this parameter. So also this observable is important in order to constrain the scalar potential and the parameters from the scalar potential. The current experimental measures from Atlas and CMS are this. And our model prediction is this, very close to the experimental report. If we see here, this plot says us how is the behavior of this model prediction when we move this beta parameter. This beta parameter, maybe if we go below, I don't know what happened. Sorry. Maybe it's
maybe with the keyboard. Maybe with the keyboard.
And you click. Conectar la antena. What is?
Maybe. Right. I press a button here. Sorry. No. This beta parameter is related with the strongly coupled underlying dynamics of the strong sector. So this beta parameter have influence on the, for example, masses of the vector resonances. So there is important to see how the model predictions behavior in this with respect to this parameter. So here we can see that the the big corrections comes from the sector with very tiny vector resonance masses, tiny respect to the energy scale, of course. But in the region in which these guys take a good behavior, from here we have very small dependence on the beta parameter. Okay. Another phenomenology or another result that is important is to study the lepton flavor violation processes. In this case, we have through the interaction, if we go below here, this interaction is very important for the flavor physics because we have a non-standard model interaction between neutrino and leptons, and Majorana, heavy Majorana neutrinos, and strongly coupled scalars. This is this new sector. So this kind of interaction have influence on processes that violate the lepton flavor in the initial and final states, like mu decaying into electron and photon, or mu decaying into 3 electrons, or this mu to electron conversion. This is the rate in which muon in the presence of a nucleus can convert into an electron because of the presence of this nucleon. It's a quark interaction, right? The importance is that these three processes are being there are very serious searches of signals of these processes. For example, the currents bound for these processes happening, we have MEC2 that says that the branching ratio for this mu to a gamma is below 1 for times 10 to the minus 13, and also for the another processes. And we have future sensitivities of these experiments. So there are a parameter space zone in which we could have a signal for one of these processes. If we see here, the lepton scalar and Majorana neutrino interaction allows radiative this type of processes, right? In our model, if we explore the parameter space, we see that we have a zone in the masses in the parameter space of masses of the charge scalars, visible charge scalars, and the heavy Majorana neutrino, in which we could have some signal from of and in this case mu to E gamma, right? But if we see this plot, we also see that there is a space in the parameter space in which we could have signals of the 3 main processes, right? So there are a relevant parameter space that can be proved in future searches of these processes. Another future that we can discuss is leptogenesis. In this case, the neutral scalars can decay in a non-equilibrium in non-equilibrium and generate some CP asymmetry. If you see here these visible scalars can decay into 2 leptons, generating CP asymmetry. These guys are mainly triplets or bidoublets because are related with the sigma bidoublet. Sorry, not triplet. And this asymmetry is induced, but then because the interaction again between strongly scalars and majorana neutrinos and leptons, right? The CP asymmetry can be computed like this, and we perform estimation in the strong washout regime, because these asymmetries are very huge. So we are in the strong washout regime, and we can prove that there is a parameter space in which we can have a compatible baryon asymmetry with the observed parameter by Planck. Okay. Another very interesting phenomenology from this model is to prove a scenario, a distinct scenario in which we could accommodate this 95 GeV diphoton anomaly. In the last years, Atlas and CMS have been report an excess of event in the diphoton invariant mass around 95 GeV here. It's important to say that this anomaly is not above 5 sigmas yet, but it is an important anomaly that can say us, it is confirmed that there is a new scalar with mass lighter than the standard model Higgs. This is very good. If this is confirmed, we can confirm that there is an extra scalar sector that we doesn't have in consideration in a standard model. It's a very good signal of that. The relevant observable is this diphoton signal strength that we can compute, and the experimental value for this excess is this from CMS and Atlas. As we were saying, this scalar resonance will be a direct hint of an standard Higgs sector. In our model, we could set a scenario in which the H3 scalar, and a scalar that is mainly a singlet, the sigma singlet, could be a scalar with mass near 95 GeV in order to see what happened. And this is distinctive from a Higgs scalar, because this is mainly singlet, it's not a doublet. And the dominant contribution for this diphoton signal comes from the vector-like fermions and the heavy inert scalars. So if we see this graph, we can see the value for this signal in terms of the masses of the charged scalars and the coupling between the sigma field and the charged scalars. So we see that there are regions in which we could agree with the signal report by CMS. Also in some masses for the charge scalars, and also for some values for this trilinear coupling, right? So conclusions for this model. We have proven that this model is phenomenologically viable, a realization phenomenologically viable of a strongly coupled linear model, participating in the fermion mass mechanism. That this is a new contribution of this. The model shown to be consistent with the precision Higgs and electroweak observables, and the parameter space is compatible with projected signals of lepton violation processes. Also could explain the baryon asymmetry of the universe, and the scalar sector contains a viable candidate for this 95 GeV excess record for Atlas and CNS. In future works, we are going to study in more details the some observables, and attack the phenomenology of the vector resonances with more deeply. We're more deep. So thank you. And if you have questions, you can.
Thank you very much. Thank you very much, Jeremy, for the very nice and complete talk. Questions from the audience?
Both of you have questions.
I know.
First question. Okay, the model is an effective model for a strongly interacting sector at the TV scale or above that. But it seems that the main consequence of the strong interaction, which is the presence of the vector resonances, doesn't affect the low energy phenomenology, right? In other words, is there in the observable you study, is there any hint that the dynamic is strong at some point?
Very good question. It seems to be that I think that the question oh, sorry, I forgot the word, but the problem is that charge scalars and vector resonances have very similar contributions to the Higgs observables. So being this one very, very massive, we can also have the contribution of the charge scalars. I don't know in this moment. My impression is that this one, the dominant contribution is also for the charge scalars. So this is a good question for future projects, right?
Another question: do you have any dark matter candidate here? No, right?
In principle, yes, because we have a preserved C2 symmetry, and we have a fermionic and neutral and scalar candidates. But well, the project was so big in some moments, so we postponed the dark matter phenomenology.
Okay.
And because other people have the phenomenology of this, study the phenomenology of this strongly coupled scalars as dark matter and have good results. So,
they include also the vector resonance because probably the vector resonance will provide annihilation or co-annihilation channels that will be important for the phenomenology of dark matter.
Yeah, there is an article that I think that this is some of these ones that is from you.
I forgot everything.
And another one is from Claudio and you and Antonio. So you can tell me. Okay, so another question. Yeah.
So, just if I understand this correctly, because the hierarchical nature of the masses of the fermions is kind of strange. You know, we might expect that all the masses should be of order of the top quark. We are trying to find an explanation for that, just with your model.
Yeah.
But the C2 symmetry that prevents the top quark mass from being changed is that symmetry naturally arising in this model, or you put it in because you want to preserve the top quark as it is?
Yeah, that is the state. As the top quark is the only one that is naturally at the electroweak scale, we want to preserve the mass mechanism because we think that the other one fermions are wrong.
Yeah, but we want to find the explanation for first principles of the distribution of the masses, right?
No, it's not a first principle.
Or a more basic.
Yeah, the explanation. Yeah, the explanation was by some reasons the U3R fermion singlet is not charged under the C2 symmetry. Yeah.
So you're moving the question to another question.
Yeah, you have to compensate something. In this case, the good thing is that in the interaction between standard model fermions and the heavy fermions, we have some scale parameter suppression, naturally. So this is a good explanation that why the another fermions have masses so tiny in comparison with this.
Okay, and finally, just to satisfy my curiosity,
yeah.
How many real particles are you adding in this model?
Sorry?
How many mu particles are you adding in this model?
Yeah. Here we have 2, 3, 5, and 8. 8 new vector-like fermions, 1 heavy major neutrino, and 1, 2, 3 new scalars. And the vector resonance. Yeah, right. Yeah. More questions? I don't know if we are hearing the Zoom. Yeah. Right.
Yes, I have a question.
Oh.
Can
Hi.
Hi, Tesio.
Hi, Tesio.
Hi, everyone. Sorry, I don't have the option of raising my hand here. I don't know why Zoom is doing that. So I just opened the micro and speak.
Okay.
Thank you, Jeremy, by the talk. Very nice, very clear. I have a question regarding the 95 GeV excess.
Okay.
You showed that you can account for the excess in the diphoton channel. And my question is, have you tried to reproduce the excess in the other channels? Because there are two extra channels, the BB bar and tau plus, tau minus channels at the same
Yeah.
95 GeV. So have you tried, or it was not possible in this model?
No, we didn't try it, but this is very interesting to study because we have an extended scalar sector. So there is a good thing to have work for the another scalar exotic scalar. I think that we can have good results for this accommodation of the scalar spectrum. So maybe the challenge is to for example, analyze this kind of decays and the excesses. I don't know what will be the result of that, but this is a good.
Okay. Thanks.
Yeah, right. Thanks, Tesio. More questions?
Any more questions from the audience?
Okay, so
Thank you very much, Jeremy. We send the sticker for the very nice talk, very nice and complete talk. Thank you very much, Jeremy.
okay.
In the Zoom, there are no.
¿Lo cierro?
Sí, parece que no hay más preguntas en el Zoom, no, solamente estaba, no, parece que no.
No.
Ya se selló.